Welcome. Today I'm going to talk to you guys about accelerations. We've mentioned it a number of times in class, but we haven't really talked about it in specific yet. And it really is about changing velocity. So any ways that you can change a velocity, there you got an acceleration. So to do that, though, we have to talk about two topics that we haven't really spent a lot of time talking about yet, and that is the comparison. The first one is the comparison between average velocity and instantaneous velocity. So far we've been really focusing on average velocities. Basically, you start with your ending position and you subtract your final position or your initial position, and you divide that by the time. And we don't really care what happens in between those two positions. And that's okay. That's good general information, and it's useful in everyday life. But oftentimes it's more important in physics to be able to know how fast you're going right now. In one of my earlier videos, I talked about the fact that you and police officers definitely want to know how fast you're going at any one particular time. So instantaneous velocity is actually an important thing to remember. Don't forget, when you're thinking about the terms themselves, average doesn't really tell you how you did. Like an average test score doesn't really tell you how you did on every test. It tells you, in general, this is how you did. Instantaneous has the word in it, instant, right here. And so you want to think about that. How fast are you going this instant, right now, is really the goal for it. Now, let's just look at the example here. I've got two number lines. And on these number lines, I have, at least the first one, I have an initial and a final position for an object. So let's say you have a bug. Okay, because physicists love bugs. I told you about that. It starts off here at the half-meter mark, and then it ends up here at the 2.5-meter mark. And it takes 4 seconds to get there. How can I figure out the average velocity? Well, you guys are totally experts at this now. I could go ahead and come over here and say, all right, well, I know that the velocity is equal to the final position. Right here, it's 2.5, minus the initial position. Right here is 0.5, over the amount of time that it took, 4 seconds. So 2.5 minus 0.5 gives me 2. 2 divided by 4 is 1/2. And so 0.5 meters per second. Does that tell me anything that it did in between those 2 points? No, but it does tell me in general terms how fast it was going on average. So that's the average velocity right there, 0.5 meters per second. Again, useful, but not very useful in terms of describing how velocity changes. So to do that, though, we need the instantaneous velocity. So I want you to see what this might look like. So the object, the bug in this case, actually did have these positions if I show you where it was at every single second in between 0 and 4. So if you look, it started out at the half-meter mark, and then it moved to the 3/4 meter mark. So in general terms here, so here we've got this, it moved 0.25 meters in 1 second. So notice that its velocity here was 0.5 meters per second. Here, notice it moved 0.25 meters per second. So we can see that obviously there's the average doesn't tell us everything specific about the what's going on in the situation. Okay, so let's get to defining acceleration. Acceleration is actually the amount of change in the velocity for every second. So as you might imagine, you can have things like average accelerations and instantaneous accelerations too. We're not really going to worry about that in this class that much. We're going to try to focus specifically on constant accelerations. So how fast is, or how much is the velocity changing every second? Now, here's an important point we're going to talk about in a minute. Velocity is a vector. That means it has to have a direction. So this is talking about any change that you might have. So any change could be speeding up, or slowing down, or changing the direction, because velocity is a vector. The direction counts, so acceleration must also be a vector. So don't forget, it is a vector. And so it must have a direction. Now, the way that we calculate this is with our next formula. So here we have our third formula for the class. It's the average acceleration formula. So the acceleration, A, is equal to v sub 2, which means the final velocity, minus v sub 1, which means the initial velocity, over the time that it takes to change. So again, the final velocity minus the initial velocity over the time that it takes to change. Now, this is an important point. If you have a subscript there, we're talking about something that happens at a specific time And 1 and 2 would tell us that the 1 subscript happened before the 2 subscript. So just keep in mind that when you see subscripts for velocities, you're actually talking about instantaneous velocity. You're talking about how fast it's going right now. And so that's going to be important. Can I plug in this velocity here? Can I take this velocity formula and plug it in? V equals, let's say, x2 minus x1 over t. Can this v go in here? Absolutely not. This is an average velocity. These are how fast it's going at specific times. So this doesn't tell us any information that's going to help us figure out how much the acceleration is changing. Why? You saw before on that number line, it doesn't tell us anything about what happens in between. All it tells us is what happens at the beginning and what happens at the end, and then compares those two. So this is the average. We cannot use it in this formula. So don't confuse the fact that that is an average velocity, and these are instantaneous velocities. Now, it oftentimes happens that the instantaneous velocity at the beginning is 0. Oftentimes we will launch things or start things from 0, and so oftentimes we can get rid of that, which is nice. But it's not always the case, so just keep that in mind. Sometimes we will slow things down, and so the initial velocity might be high, but then the final velocity might be 0 as something slows to a stop due to the action of friction. So that's a possibility too. Okay, so now because acceleration is a vector, we can talk about what direction it goes in. So take this example for a second. We have an object that starts at the 0 line because I can choose where the frame of reference is, so that's where I choose where it starts. And it already has some velocity. So it's already moving to the right, okay? So it's moving to the right, and as time goes by, we see where its positions are as it moves across. So here it is where it starts. Here's where it is at the next moment in time. Here it is where the next moment in time is. There it is where the next moment, and the next, and the next. And so this is where it stops moving. So you can see what happens to the distances between, or the displacements for each interval of time actually get smaller and smaller and smaller. So which direction is the acceleration actually acting? Is the acceleration acting this way? Is it speeding up in this direction? No. It's changing its motion in this direction. It's actually slowing down. So its motion is this way, but its acceleration is this way as it slows down. And so if we were going to, we could write an acceleration vector that looks like this to let us know that the acceleration is going in this way. So here's a helpful hint. If the acceleration and the motion are both in the same direction, then it must be speeding up. If the motion is in a different direction from the acceleration, then they must be slowing down. If they're completely different directions, like 90-degree angles and things, we'll talk about that later on. That's for second quarter, so don't worry about that. So that's the acceleration must be slowing the object down in this case, so it must be acting opposite of the direction of the motion. So now we get to a crucial part, and it's one that I think people get confused about all the time, and that is, what are the units for acceleration? So you have to remember what the definition is. Remember, the definition for acceleration is how much the velocity changes every second. So the velocity, this is the formula in its shorter form, right? So the change in the velocity per second is what I'm talking about here. So if you look at the units for velocity, the units for velocity are meters per second. And we're talking about how much the velocity changes every second. So we end up with meters per second, which is weird, right? So we write it like this: meters per second per second. Now, I don't know about you, but I am lazy, and so that looks kind of weird. And so sometimes I don't really like to use that because I don't know, it's a lot to write and it looks kind of strange. And it can get kind of confusing. So there's a way to make this a little bit simpler, and I'm going to show you how to do that now. This actually means, I'm going to rewrite it over here. Meters per second actually means meters per second divided by seconds. Now you might remember from middle school or late elementary school that when you divide by a number, it's really the same as multiplying by its reciprocal, right? So I'm going to go ahead and take this and erase it like that, and I'm going to say multiply by the reciprocal. What's the reciprocal of s? It's 1 over s. So I'm going to go ahead and do 1 over seconds here. So now I'm multiplying. Now remember, when you multiply fractions, you multiply straight across, right? M times 1 is M. S times S is S squared. And so the easier way to write the units, the lazier way to write the units, is meters per second. Now this is not a big deal, but I just want to point out that there's a couple of formulas that kind of wrap everything together, and they're super, super helpful. So I'm just going to introduce them now, just going to show them to you. We're not going to do any examples in this video, and we're going to work on it in class together so that you guys can have a better sense of how to use these. The first formula right here is what I like to call the master motion equation. Why? Because it has basically almost everything that you would want in a motion equation is in there. So it starts off by saying the displacement, right, the change in the position, is equal to the velocity that the object starts with times the time that it takes, plus 1/2 times the acceleration that it experiences, multiplied by the time that it takes squared. This time right here and that time right there, both the same amount of time. So this is when you want to try to figure out where something ends up if it has some initial velocity and is being accelerated. The typical example we will use in the class is how far something falls. When something falls, gravity accelerates it downward, and so we'll use the gravitational acceleration and the time that it takes to fall to figure out how far it falls. Just an example. The other equation is a little bit trickier. It says the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. Again, displacement is the change in position. Why do we need this one? Because it has two things that this one doesn't. Or I should say, it makes two big changes. This one, you can see, has a final velocity. So sometimes you need that. This one does not. Okay? Also, this one has time. This one does not. And so if you're saying to yourself, what the heck, which one am I going to use? If you have no time, use this equation, which is what I call the no time formula. So I would say use the no time formula. If you have time and you do not worry about the final velocity, then you can go ahead and use the master motion equation.